Hi, in our previous video, we explored how AI improves physician accuracy in detecting abnormalities on chest x-rays and the significance of the AUC metric in evaluating model performance. However, one of the biggest challenges in training AI models for medical imaging is class imbalance, a problem that, if not properly handled, can actually lead to poor generalizations and unreliable predictions. Now, in this continuation, we will investigate the problems encountered when training AI models for classification and image analysis and understand the class imbalance problem, how it affects AI model performance, and the multiple techniques that can be used in order to mitigate it. Now, in most real-world medical data sets, the number of normal x-rays far outweighs the number of abnormal x-rays, and this is because disease prevalence is naturally low compared to healthy individuals. So, for example, say we have approximately around 100,000 x-ray data sets, and 95,000 may be labeled as normal, while only 5,000 may be labeled as disease or abnormalities such as pneumonia or even lung cancer. The AI model, therefore, if not trained without any adjustments, may learn to simply predict normal most of the time, which would lead it to approximately achieving around 95% accuracy, which I think is pretty high, while also failing to detect disease cases most of the times accurately. Now, this results in an extremely high false negative rate, wherein the patients with diseases are missed by the model, which makes the model clinically unreliable. Now, in order to solve this problem, we first need to understand it. And one key bit of information that's crucial to understanding the problem is the loss function, which is used in model training. Now, the most commonly used loss function in medical classification tasks is the binary cross-entropy loss, which measures how well a model predicts its probabilities for two classes, such as normal and abnormal. Now, let's move on to look at how the binary cross-entropy loss function actually works. Now, the binary cross-entropy loss function is computed using this formula, and something we have to note is that P represents the model's predicted probability for the disease actually being present, and Y is the actual label value, and 1 and 0 respectively represent disease and normal. Now, let's look at two example scenarios. First example scenario, we're predicting a cancerous mass. So, since it's an actually cancerous mass, then the actual label in this case would be 1. And when we substitute that to the Y value, we will be using the first part of this equation. Now, let's say that the model, for instance, has approximately 20% confidence that this is a cancer image, and therefore for P, we will have the value 0.2. Now, when we compute it and put it into this equation, what we have is minus log 0.2, which then is 0.7. So this is a pretty high loss, which means that the model is penalized and must adjust its parameters. Now let's look at the second example scenario where we're predicting for a normal image. Since we're predicting for a normal image, since the actual label value would therefore be 0, we will be using the second part of the equation. Say that the model predicts has 80% confidence that this is a mass sample, which means when we actually put that in there, we will have the same value, the same loss that we got from the first scenario. Again, the model is penalized for incorrect prediction, and the loss function outputs a value for the cancerous mass prediction and the normal image prediction, and that value is essentially the same for both predictions. Now, then, the reason why this is problematic is because, we'll say that we have approximately 4 samples, and 3 out of these 4 samples are normal and 1 is cancerous. The total loss from the cancer samples is 0.7 because we're multiplying 0.7 by 1 because we only have 1 cancer sample. But the total loss value coming from the normal samples is 0.7 multiplied by 3 because we have 3 normal samples, therefore the total loss value is 2.1. Now, because the contribution to the loss is coming more from the normal samples rather than the cancerous one, the algorithm is optimizing its updates in order to get normal examples and not really give much relative weight to these mass or these cancer samples. Now, the problem with that is that it generally creates a bad classifier. Okay, now that we understand why the problem is so and why it is problematic, in our next video we'll be looking at the ways that could be used in order to solve it.